Hello and welcome to our next set of stats notes. We are moving into chapter 7. We're going to cover some pretty important ideas for statistics in chapter 7. You'll see chapter 7 ideas come up over and over again for the rest of this semester. So we'll keep coming back to things we've learned in chapter 7 throughout the rest of the semester. So just to kind of give you a heads up, this is a section, a unit, a chapter, I should say, that is really, really important for you to understand and be able to use as we progress. So I'm going to try and definitely, share this as clearly as I can and make sure you hopefully understand it well. If need be, you should definitely spend some time reading the textbook, maybe watching other videos. Remember, there's links for other videos in my lab beyond just mine if you need additional help understanding the subject, but it's something that we'll use throughout the rest of the semester. So we talked about how so far we've been learning all these ideas about statistics, and then we've been progressing and making a shift into the idea of inferential statistics, which is where you take a sample and then you can make some kind of claims or assertions about the entire population, the whole group. And that's what we're really doing, making that shift now in this section. So one of the big examples would be if you want to do some kind of survey about U.S. residents and maybe you want to determine the proportion is just a fancy word for percentage, or what percentage of people have health insurance. So what we would do is we take a sample and we find the proportion or percentage of the sample. We call that the sample proportion. And we're going to work with percentages exclusively in this section, and 7.2 will kind of shift and we'll talk about how to deal with means. So we'll see a lot of proportion in this section just because proportions are easier, so we're starting with them. We'll start with the easy stuff and work our way up a little bit. So the proportion of the sample is called the sample proportion. So it's just the proportion that have what you're looking for. So here we were looking for people to have insurance. So the percentage of our sample that had insurance is called the sample proportion. Now that is not necessarily equal to the proportion for the entire population, right? So my sample might be like 45%, but we might find out the whole population it's actually 50%. And I just randomly picked a sample that had a little bit less people in it that had health insurance than the actual population does on average, overall. So we use this to try and kind of estimate or get a good idea of what the population value is, and that's why we will call the sample proportion or use the sample proportion as what we call a point estimate. So I take my study, my sample data, I collect it, and I say, hey, I got 45%, and I say, okay, so 45% is my estimate, my guess for what is for the entire population, because at this point I don't know what the population value is, but my 45% helps me get a good guess of what it should be. A lot of times that's the best I can do is take a sample and think, okay, for my sample, what do I expect the real value to be? Well, I expect it to be close to 45%. Might be a little bit below, might be a little bit above, it might be the same. I don't know, but I think it's going to be around 45%. So this is what we're doing, and we're going to do this with means. We're going to do it with other stuff. It's pretty the common technique. Take a sample, collect a value, get data from that sample, and then use that as an estimate for the overall value. Okay, so more terminology. We're going to use the letter P to represent the population proportion. So P is the population proportion. So this is the percentage for the entire group. So this is that 50% I was referring to, where 50% of the whole population has health insurance. So P would be that 50%. Typically, it's something we don't know for sure. Usually, we're trying to estimate or kind of make guesses about P. In certain cases, someone might give you P, and that's awesome, and then you can work with it. But most of the time, we're trying to guess about it. And then the percentage of people, so then we use P hat to represent the sample proportion. So P hat, you put a little hat over top of it, that is the sample proportion, and it is the proportion from our sample. So this is where I did my sample. I said, oh, my sample only had 45%. Well, that wasn't very close to 50, but it's close-ish. That value is my sample value. It's my value you're going to use to try and guess what the real value is, trying to get an estimate of the real value. So I know the real value because I told you it's 50%, but my example, my sample value is only 45. Sometimes your sample's a lot closer. Maybe you'll get like 49, 50% of your sample, but you never know for sure, usually. So we're going to estimate P, the population value, with P hat, the sample value. Since we're dealing with proportions, we're dealing with percentages, the calculation for computing them is pretty easy. To find P hat, the sample value, we just take X, which is the number of members in the sample that have the attribute we're looking for. So in this case, it would be like health insurance in my example. And N is the sample size. So the X is the number with attribute. So they have whatever you're looking for, whether it's that they have health insurance, they own a home, they are married. You know, if you're doing studies on any of that stuff, that's what you'd be looking for. Is, you know, do they have that? X would be the number of successes or things that do have that, and then N is the number sampled. And if you divide those, you'll get your proportion, your sample proportion, p hat. So X will always be smaller than or equal to N. You know, the most it could be is N, because that'd be like if everybody had it. So I did a study and everybody had health insurance, I'd have 100%. Probably not going to happen, but you know, if it did, that'd be the only time X could equal N. Typically, X will be smaller, and you divide, you get some kind of decimal, which will turn into percent. So we like to call X the number of successes. You know, it's the number of people with the attribute. Remember that success is kind of misleading, because you might think that, well, that's always got to be the people with insurance, health insurance. No, it could be the people without. If you're doing a study where, you know, you're looking at how many people don't have health insurance, then X could be the person who doesn't. Or remember, it could be like how many people did the drug actually harm, you know, had bad side effects. Well, then the, you know, has bad side effects would be what you're looking for. So success just means they have the attribute you're studying, they have what you're looking for. And then N minus X, well, that's going to be what's left over, right? If you take a number that have it and it's, you know, subtract that from the total number, you end up with people that didn't, and we'll call that the number of failures. Again, kind of misleading, because if the attribute you're looking for is, yeah, the medicine did bad things to them, then X would be the number of people that it did bad things to, and N minus X would be the number of people it didn't do bad things to. So just remember that X is what you're looking for, and N minus X is the how many didn't have that, or what's left over. Okay, so when we're doing proportions, you know, we'll do surveys like this. We'll survey 1,000 people, which you'll notice will be your N, right? That's your sample size, because that's how many people you surveyed. And they say, what's the sample proportion if 856 participants, had health insurance? Well, that makes this X, because it's the number that haven't, right? Well, p hat, which is your sample proportion, right? That's p hat, is the percentage of the sample, is X over N. So we just take the 856 people that had the health insurance divided by the 1,000 people we surveyed, and that would give us our answer. So this one would be 0.856, or 85.6% if you want a percent, right? So that would be the percentage that had health insurance. This is your proportion in this problem. Now, in real life, we can't just say, oh yeah, I did a sample and I got 85%, so I know of the entire population of the US, 85% people have health insurance. No, because we only sampled a small group. We only sampled 1,000 people. There are millions and millions of people in the US. So our sample of 1,000 is just a drop in the bucket. And even if it was a bigger drop, we still wouldn't be able to know for sure what percentage of people have health insurance. We know it's probably going to be close to 85%, because it's a fairly decent sample. 1,000 is big. I mean, remember we said in the previous section that samples bigger than 30 are usually good enough. So this one's big enough for sure. And so the answer should be close to the actual percentage, but we don't know how close. We don't know what the exact answer is. The exact answer might be 80. It might be 90. We don't know. It's going to be probably something close to 85. You know, it could be even closer. It could be like 87. But 85.6 isn't the exact right answer. It's just an answer that helps us get an idea of what it should be. So the real population percentage is going to be somewhere probably close to that 85%. You know, because our small sample should get us close, but we don't know exactly what the right answer is. So this section is about taking the sample value we get, using it as an estimate, and building later what we'll call confidence intervals, and basically building a kind of an interval where we say, okay, within this range of values, we can be pretty sure, pretty confident that we've actually gotten the right value within that range. That's kind of what we're looking for. We want to say, okay, I took my sample, got a value. Now I'm going to be pretty confident that it's going to be, you know, the real value is going to be kind of within this range of values. It's going to be this range. That's where we're working towards. But to do that, we have to be able to calculate our sample proportion. So again, sample proportion is number of successes divided by the number sampled, sample proportion. Okay, so here we have confidence intervals. So we take our point estimate. So your point estimate with this chapter 7, is the value you get from your sample. So I took a sample, I got a value, I use that as an estimate. We'll call it a point estimate because it's just one number, it's one point in the scheme of things. And then we'll use it to kind of make an estimate about the parameter. Remember, parameter is the value for the entire population. So that's what point estimates are for. So point estimates, we use those to estimate the parameter. Since different point estimates can be obtained with different samples, meaning if I go back and take a different sample of 1,000 people, maybe instead of 85.7%, I'll get 87%, or maybe I'll go back and I'll get 84%. You can get a different estimate when you use a different sample. It's important to have some way to kind of judge how good the estimate is. And we do that providing a confidence interval. Confidence interval kind of gives a span of numbers, and then we'll tell people the level of confidence, how confident we are. So that's why we're going to build these confidence intervals along with the point estimate. And that way people can figure out how accurate our result is and kind of get an idea that there's kind of a window of options. It's not just one number that's probably right. So a confidence interval is always going to be a range of values. It is an interval of numbers. A confidence interval is a range of values around the point estimate. The point estimate you get is always going to be right in the middle of your confidence interval because you have to have the idea that maybe the value is above or below. So the confidence interval is going to be around it. And it's an interval where we can be fairly certain that the actual parameter is in that interval. So we're kind of making a window and then saying we're going to be pretty confident that the window of values we have contains the real value. The confidence level or degree of confidence, those different names for the same thing, is the probability that the confidence interval contains the actual value. So it's the probability that it contains the actual parameter. So for example, if you do a survey, it shows 48% of people have health insurance. So that was your sample, right? Your sample value is 48%. And you build a 95% confidence interval that says you're 95% confident the interval, the value is between 45 and 51. Then you're saying there's a 95% chance, this is pretty high chances, right? 95% chance that the real number, we don't know what it is, but somewhere close to 48, but we're 95% the real number is within that range. It could be 45, it could be 51, it could be 47, it could be 48. We don't know what it is, but we're 95% sure it's going to be one of those numbers in that range. And that's pretty good, right? Because then when someone looks and say, okay, well, if I'm doing my, developing a thing to help people get health insurance, then I know starting-wise that I can expect close to 45 to 51% to have health insurance. That tells me about half people have health insurance, and I can expect half people don't because you've done this survey and figured it out, and they're 95% confident. And so then they can use that information. Now they might not need to know exactly what the percentage is, but knowing that it's somewhere between 45 and 51, they know to expect about half of people to have health insurance and about half not to. So this picture kind of shows how this would work if you took lots of samples. So here they took 20 different confidence intervals. So they took 20 different samples and built confidence intervals for each sample. So the middle of each of these lines is going to be a little sample result. So they got one result right there, got one result right there, got one result right there. And so these are the middles. Each one of those was a different sample result. And then they took those and they built these confidence intervals to kind of get an idea, okay, what is the actual value? And so they built the confidence interval. And they show how, since in this case the actual value was actually 50, almost all of these include it in somewhere in there, even though they got this value. Because 50 is so close, they're pretty close, it's in their confidence interval. They got this value at 50 still in there. They got this one 50 still in there. Even though that one was kind of high, it still included 50. There's only one example that missed. This one, somehow they picked a bad sample, and it's by random chance, right? They didn't know they did it. They just picked a sample and intended to be a bad one. And so this one's so bad that the actual value is way up here. And so this sample was so bad, it actually makes it look like, the value should be below that. But 19 times out of 20, only one was bad. They actually got pretty close to the actual value of 50%. So the rest of them all contain that value. So that's the thing. The confidence intervals, if we build them, 19 out of 20 times, because 95% of the time, they are going to be good enough. They're going to include the real value. Only 1 out of 20 is going to not, and that's fairly rare. So the chances of that happening are very slim. Okay, so this is the idea. We're going to get into this here as we go. We're going to build these confidence intervals from our estimate. We'll take our sample data, create our estimate, and then build this confidence interval. Before we get too far into that, we want to talk about alpha. So alpha is the probability of missing the parameter value. So alpha is kind of the opposite of a constant. Instead of being 95% confident we got a value, alpha is the confidence that we kind of missed the value. So alpha is the probability of missing. So if we're 95% sure that we hit, then alpha would be like the 5% chance of missing. So the opposite of alpha, 1 minus alpha, would actually be our confidence level, how sure we are of hitting. So this chart kind of shows, so if you have like a 90% confidence level, so you're 90% sure that you got it, then your alpha would be 10%. There'd be a 10% chance that you missed. Now we typically split alpha into 2 parts, and we'll see why we get to some pictures and charts later. So most of the time we won't actually work with alpha, we'll actually usually work with alpha over 2. So we'll take the 10% that we have of missing and split it into 2 5%. And then we're going to talk later about critical values, so we'll talk about that later, how there's z-scores that go along with these percentages. 95%, if you have a 95% confidence level, means you're 95% sure you hit, then the alpha is going to be 5% because you have a 5% chance of missing. And then if we split that into 2 pieces, 2 equal-sized pieces, each one's going to be 2.5%. So this is 2.5%. So we take, okay, the 95% sure chance that we hit and split up into, and then the parts that we missed are going to be 2.5%, 2.5%. There's 2.5s. If you do a 99% confidence level, so you're 99% sure you actually have the right value in the interval, there's a 1% chance you missed. There's still a chance you missed, and that means there's only a 0.5% chance in each, of the 2 pieces. So we split that up. These 3 are the most common. So in real life, if someone's doing statistical study, their confidence level should be either 90, 95, or 99. If they're using anything else, that's when things get a little fishy. You start wondering why they're using something else. If someone's using something like a 92 or a 97, that'd be really fishy, and you start to think maybe they're trying to make themselves look right or look better or something. Maybe they're trying to skew the data. You really should only see people using 90, 95, and 99. The reason we have 3 different values, well, if someone doesn't need to be as confident, maybe they don't have to be quite as careful, they might use a 90%. Usually it means that you end up being able to take a smaller sample. A smaller sample means that you have to spend less. You don't have to spend as much money. So if you're in a situation where you just want to have a decent value, but you have to be really, really precise or really, really accurate, you go at 90%. 95 is kind of the gold standard, the standard typical. That's what people do most of the time. And then every once in a while you get someone that needs to be really accurate, like they need to be really confident, and they'll do a 99%. That's like your NASA trying to make sure the parts they build for the rocket are really, really, really safe and secure, and they don't end up killing their astronauts. They'd be the ones that do like a 99% interval. But everyone else is probably going to be like doing 95, 90. So those are the 3 common ones. Okay. So let's talk about this. So to build our confidence interval, to make our range of values, we're going to use what we call critical values. So the critical values separate the kind of standard, typical, what we expect to get from the significantly higher low values. Remember we said significance is that stuff where it's like it's significant because it's rare, we don't expect it, it's way out there. So we're going to have stuff that's outside the confidence interval is going to be our significantly higher low stuff. The stuff that's so high, it's a high number or low number, we just kind of don't really expect it, that's going to be outside the confidence interval. And the stuff that's not significant, the stuff that we kind of, okay, we expected that'll be inside the confidence interval. So not significant is inside the confidence interval, and significantly higher or low is going to be outside the confidence interval. And the critical values make the separation, separate the sample statistics that are significant from not significant. To do that, to find these critical values, we're going to use z-scores of alpha over 2. Remember, alpha over 2 is that half of the missing probability. Probably missing, it will take a split in half. The reason we have to have half is because, again, we're going to split this into both high and low. So that's why we end up with half like this. So the z-score, alpha over 2, the z-score that corresponds to alpha over 2, is the critical value that separates the normal distribution, we're going to be working with normal distributions like we like to, into area of 1 minus alpha in the middle, which is going to be the confidence level. So this is going to be the middle region, is going to be your confidence level. That's going to be the percentage, or 1 minus alpha. And then the regions outside on both sides are going to be alpha over 2, because we're splitting it up into 2 halves on the 2 sides. So if you take the 2 sides together, that'd be a probability missing, because we're going to have the really unlikely low values, really unlikely high values. In the middle, we're going to have the values you expected. So your confidence level would be in the middle. This would be like your 95%. And then take your 5% and split it between the 2, because that's what's left over, the missing parts. The parts we're not going to really worry about those because they're so extreme. But since we have 5% between the 2, each one ends up being half of that. So we end up with 2.5 on each value. So we're going to use z of alpha over 2 to find the z-score that marks off this region, where we're going to say ignore those values that are really high. And then to actually get the low value, we're just going to take this one, because this is a standard score, a standard normal distribution with 0 in the middle. We could flip it over and do negative z of alpha over 2. Because remember that there's symmetry here. So if there's 2.5% here, there's 2.5% there. These z-scores are going to be symmetric. One's going to be positive, one's going to be negative. So that's what we're looking for. We're going to say most of the values in the middle, we're going to kind of get rid of these unlikely values. So when we're 95% confident, we're just not really worried about the last 5% that's split up between the 2 ends. Okay, to find these critical values, we're going to use either a table or technology. We'll mostly use technology because we've seen that that's a lot easier most of the time. And we're going to find the z alpha over 2, which is the z-score with an area of alpha over 2 to its right. So that's what that means. Remember, alpha over 2 to the right. And then we're going to find negative z of alpha over 2, which is going to be just the negative z-score. So we're going to find both. But this one, once you find this one, you can just make a negative and you got the other one. So it's not too hard to find the negative one, because you just find this one and then make a negative to find the other one. These values are based only on the area, and the area is the area outside the confidence interval. All you really need to know to find these is the confidence level. So as soon as you know which one you're working with, whether you're doing 90, 95, or 100, you can just find those values. You don't have to know anything else. So we can determine critical values just from the confidence level of our confidence interval, which is why on the previous page, they actually already gave them to you. So if you noticed here, they already told you 90% confidence level, what's the critical value? What's 1.645? And then the negative z alpha over 2 would be the negative 1.645. That'd be the other one. 95% confidence level, that one's going to be 1.96. You notice because the percentage went up, that we're going further out. We're spreading out the middle, and so then we have to go further out our z-score. So it's like if we take this one, 90%'s here, and then 95%'s here, so you can see the z-score is going to get bigger because we're getting further out. So 99 would be like way out here. And so that's why 99 is even bigger. It's all the way out 2.5. So negative 1.96 and negative 2.575 would be the corresponding like negative z-scores. So for these three, these are really well-known numbers. I believe they're even on your table. So if you're doing z-scores, you have a 95% confidence level, you see the 1.645, it's the same one. That's that same 1.645. And then they have a 99.51, which is the 2.575. And so that's what this one is. So 99, and there's the 2.575. So those are two really common ones. You'll see 95, 90%, 90% are even on your chart. 90% is not on there. So that one you'd have to maybe, if you wanted to write it on your note 3x5 note card if you need to do it. But we'll show you how to find these just in case. So if you forget what they are, if you didn't write them down, you can find them pretty easily. So let's go ahead and find them. So let's find, we'll do it for 86% just so we get a different number, but this is the same idea. So what we're doing is we're finding if we have a normal distribution and we want 86% in the middle, then what are the z-scores, right? The z here and the z, negative z here, that will do that for us. Again, to do this, we're going to say if there's 86% in the middle, then we take 100 minus 86%, or 1 minus 0.86, and we see there's 14% is alpha, as the two regions together. So if I divide that by 2, alpha over 2 is going to be 0.07, or 7%. So each one of these regions is going to be 0.07. So that's just taking the 86%, saying, okay, well, what's missing, 14%, split that in two, we got 7%, or 7%, because 0.07 is the same thing as 7%. So that's what this is, just 7% in each end. So we have 7% in each of these ends. We're looking for the z-score that does that. So I want the z-score that has 7% to the right or 7% to the left. Now, if I'm going to use the calculator, remember to use the calculator. If we have an area and we want to find the z-score, we use the inverse norm option, right? So that was that. You hit this second button in distribution, and you have inverse norm. Inverse norm is for finding, if you have the area, find the z-score. So here, I'm going to do this. What I'm going to do, I'm actually going to put in 0.07. And I'm going to put a 0.07 here, and you'll see what happens when I put 0.07 for my 7%. The mean and the standard deviation are going to be 0 and 1. So I'm going to put 0.07, 0 and 1. Remember, this is your mean, and this is your standard deviation. And it's going to give me the negative 1.475. Because remember, your calculator always does area to the left. So what it actually did is I actually found this value. I actually found the negative z alpha. So this would be negative z alpha over 2. So this is negative 1.475. Well, I don't really care whether I find the positive one or the negative one. It's 476 if you run that. Because I don't really care which one I find, because once I have one of them, I can just change the sign and get the other one. So once I found the negative z 0.07, then I can get the positive one just by changing the sign. So negative z 0.07 is negative 1.476, but positive z 0.07 is 1.476. And that's what they're looking for. So those would be the critical values. So those are the z of alpha over 2, both the positive and the negative z of alpha over 2. So this is the idea. So if you know your confidence level, if you know how confident you need to be, here we're being 86% confident, which you wouldn't really do very often. You'll get some homework questions because they want you to do ones where you can't just look them up on a chart. So they're going to be probably like this, where you find the critical values, and again, you're marking it off, and you're finding the region here. We're going to use this then later when we go to create the confidence interval, because this is going to give us our cutoff points for our confidence interval. We're going to use these numbers to figure out our cutoff points, like how far left and right do I go kind of thing, to build a confidence interval. So we'll take our point estimate, use our critical values, and we'll figure that out. So again, critical values, we're worried about like what's the area in the middle, and then we can subtract that from 1 to get the areas that are on the outside, so divide by 2 to get just one side, and then inverse norm will let us know what the z-score is for that side. And again, if you get the negative value, you can just switch and get the positive, because these are always symmetric, because we're doing standard normal distribution with 0 in the middle. Okay, so now we got critical values for this information. So you can look at those critical values. Now we're ready to talk about margin of error, which we'll use those critical values to make our margin of error. So the margin of error is kind of the amount of error you expect based on how big your sample was. So the bigger your sample is, the less error you're going to have. We're going to see that the bigger your sample is, the closer your value is going to be to the real value. So if I do that, study where I sampled people, said, hey, I got 46% from my sample that have health insurance. If my sample is pretty small, if it's only like 100, maybe 1,000, versus if my sample is like 10,000 or 1,000,000, I'm going to expect to have more error and probably not be as close. But if my sample is like 1,000,000, I'm going to expect a lot less error, because I have such a big sample, we get a lot closer to the real value. So the real value is 50%. It probably would be very unlikely that I get like 46% from a sample of 1,000,000. I'd probably get closer to like 49 or 50 if that sample is 1,000,000. So the margin of error is a measure of how much error you have. And it's basically a lot on the sample size, and then how high your confidence level is. The margin of error is the maximum likely amount of error, or difference between our point estimate and the actual population. So we'll call that the error. How different is the value you got from your sample versus the real value for the whole population? That's your error. Okay, so to find the margin of error, there's a formula for it. We'll take that critical value, so that's why we had to find critical value, because we use it to find margin of error. And then we'll multiply it times the square root of the p-hat, where p-hat, remember, is the sample proportion, the percentage from the sample, times q-hat. Well, q-hat's new. Q-hat is the proportion of failure. So instead of the percentage of success, is percentage of failure. So like if p-hat was 45%, then q-hat would be the rest of it. It would be the 55% left over. So you can always find q hat by subtracting 1 minus p hat. 1 minus 0.45 gives you 0.55. And then that's all divided by n, which is the sample size. So this is the formula for margin of error, E. Margin of error, we use E for error, margin of error. So margin of error, we're going to calculate margin of error for this problem down here. So first off, notice they give us some information. They give us x is 14, that's the number of successes. N is 40, that's the number sampled. And they tell us 95% confidence level. That's really all they need to tell us. First off, notice, since this is 95% confidence level, we know that alpha is going to be 5% or 0.05, right? That's the probability of failure, right? Or of missing, since 95% confidence we hit. And alpha over 2 is going to be half of that, so it's going to be 2.5% or 0.025. Now, because 95% is a really common known value, we can just look this one up on the chart. We don't actually have to do a lot of work to figure out critical values. We can actually take the 95% and say, oh, the critical value is going to be 1.96. So from the chart, from your t-table chart or from your previous page, the z for alpha over 2 is going to be 1.96. Make sure I wrote down the right number. Now, if you didn't know that, if you didn't look it up on the chart, if you didn't have it, you could still use the inverse norm on your calculator. So you go to that second distribution, inverse norm, type in that 0.025. And again, it's going to give me the -1, so it's going to give me negative 1.96. But for the formula, they want the positive one. So if I got this, I'd take this negative 1.95599, which rounds to 1.96, and just make it positive because they want the positive one. This should always be positive for your margin of error. Margin of error is never going to be a negative number. It should always be a positive number. So if you didn't know how to get this from the chart, you could use inverse norm with the 25%. But again, we're not using the 95%. We're using the 2.5% because that's the ends. So again, if I think of it like this way, I have 95% and I have 2.5% on each end. So hopefully I'm getting that idea of where this 2.5% is coming from. 95% in the middle is the kind of expected values we have. Split the two halves, and so we have 2.5% on each end. Those are the values we don't expect. And again, z of alpha over 2 is this one. It's the positive number, and that's what they want. Okay, we got that value. Other things we need to have p hat. But remember, the proportion you can always find by taking the number of successes, x, which is 14, over the number sampled, n, which in this case was 40. So by doing 14 over 40, we can find out what the proportion. This is the sample proportion, so it's the percentage from our sample. So our sample had a percentage of 35%, so this would be 0.35 or 35%. When you do the formula, this margin of error, you definitely want to put them in as a decimal. So that's why I'm going to put 0.35 first, because what are these decimals? So what's q hat? Well, if 35% of the time we got it, how much percent of the time we didn't get it? Well, that'd be 65, right? If we do 1 minus 0.35, we get 0.65 or 65%. That's the probability of not getting it. And the n was given, right? And it's right there. So to find the margin of error, we're going to take the z of alpha over 2, so 1.96. And so you can see this number gets bigger as the confidence level gets bigger. So the error is actually going to get bigger as the confidence level increases. That's something you'll see with this, because the more confident you need to be, the more room for error there is if you don't have a big enough sample size. Over here we have p hat, which is the 0.35, times q hat, which is 0.65, and then divide that by n. And now because n, 40, is on the bottom, the bigger n gets, the smaller this number gets. So the bigger your sample gets, actually the smaller your margin of error gets. And so in real life, if people want to decrease the margin of error, if they want to have a smaller margin of error, they'll actually get a bigger sample. But that costs more money. So that's why we still sometimes use small samples, just because it takes more time and money to use a bigger sample. Or sometimes it's hard to get a bigger sample. Maybe there's not a lot of people with what you're studying, so you can't do it. But the bigger your sample size, the smaller your margin of error will end up being. So those are kind of the two things you always think about, like my confidence level and my sample size. Those are going to affect my margin of error. How much room for error do I have? So let's type that in a calculator and see what that margin of error is for this one. It's 1.96 times square root and do 0.35 times 0.65. You don't really need the parentheses, I just put those in for multiplication purposes. And then divide by 40. Make sure that the divide by 40 is also inside the root. I always get people to type this in, they don't get the 40 inside the root. Make sure the 40 is inside the root as well. The 1.96 is the only part that's not inside the root. And I get 0.1478, or 14.78%. So because this is a fairly small sample size, 40 is not that many people. This has a 14% room for error. So that's telling us that, our value we got, which was 35%, there's actually a 14% room for error there. So the real value could be up to 14% above or 14% below. This 35 is just kind of it's kind of in the middle, but this 14% kind of measures how close, how good is our value. The bigger this is, the less useful your number is, because then there's such a big range of what it could potentially be. So you really want to try and keep your margin of error down. That's why most people are going to try and go for bigger sample sizes, because that will keep the margin of error down. But yeah, that's what they're looking for in this problem. What is your margin of error? Okay, so moving on from margin of error, the next thing we're going to do is we're going to do what we call constructing a confidence interval. So now that we know how to, we find our sample, or our point estimate, the value from our sample, we know how to find the critical values and then use those to get the margin of error. Now we can think about making our window of what the possible values are. So using the critical values and margin of error, we're going to create a confidence interval from our point estimate. So we have to have a couple requirements before you can actually do this. So you can't actually build confidence intervals unless these requirements are met. We're going to give these to you basically for this semester because this is just intro stats, but if you went to like a higher level stats course, you might have situations where these aren't met and you'd have to do other methods. We're going to basically give it to them. So most of the time it should be a simple random sample. We said that's kind of the best sampling technique. You can always assume it's simple random sample. I'm not going to give you one that's not. Binomial conditions are met. So in this case, it means that when you do this, things have to be independent. So if one thing this affects the other, it doesn't work. There's only so many trials, fixed number of trials. There's only two possible outcomes. That's the big thing. There's only success or failure. If you have a third option, can't do this. All have equal probability. And then this is the big one. This is probably the only one you might see fail in this semester, is they have to have at least 5 successes and 5 failures. So if your sample is so small that you don't have enough successes or enough failures, then it doesn't work. So like if you do a sample of like 20 people and 27 of them come out with success and you only have 3 failures, then that's not a good enough sample. You have to go back and get a bigger sample. You have to have your samples be so big that both the number of successes and the number of failures are at least 5. That's kind of the most important one here, is the number of successes and failures should be at least 5. The other ones that really won't mess with you much, you might see every once in a while, you might see a problem where you do this, and if they have not enough successes, not enough failures, you'll say, yeah, we can't use confidence intervals because we need to have enough sampled. We have at least 5 successes, at least 5 failures. If those are all met, we're going to go ahead like we did, find the critical value. And once you have the critical value, we're going to find the margin of error. And then once you have the margin of error, we use the formula. This thing right here, we're going to add and subtract the margin of error from our point estimate and find the confidence interval. So the confidence interval, it's going to be 2 values. And it's going to be a value below the point estimate and a value above the point estimate, which you'll either write as an ordered pair like this, or you might write it like this, where you take the point estimate and write plus or minus value. And you'll see these both in real life. So if you see like tolerances a lot of times, like if people are building machines, equipment, stuff like that, a lot of times they'll tell you the dimensions and they'll put a little plus or minus and they'll put how much error they have. And so that's a really common way to do it. The first one you'll see a lot if you look up like statistics, like vital statistics, like the percentage of people that, if you look up like average, percentage of people that have health insurance, or percentage of people that move to a new state, stuff like that. If you look at percentages, you'll see a lot of times ranges like this where they say between 30 to 40% of people have this or don't have that. So you'll see that for those types of situations. Before I do the next example, I just want to go back real quick. Since we know the point estimate and the margin of error on the previous problem, so up here we knew the point estimate, p hat, right, 35%, and you know the margin of error, 14%, we can actually pretty easily figure out the confidence interval, because the confidence interval, again, we just take the point estimate, so p hat, 1 through 5, or I'll put 35% maybe. We'll do that, 35%. And the margin of error, which we'll call 14, I'm going to call it 14.8 just to make my life easier. 14.8%. My lab will ask you to tell you what decimal to round to for stuff like this. And to build the confidence interval, we're going to take this amount, we're going to subtract 14.8, we're going to add 14.8, so we get 35 minus 14.8, and 35 plus 14.8. Subtract 14.8, I get what? 21 minus 0.8 is 20.2, and 35 plus 14, so I get 49.8. So this is a confidence interval. So we started off, we did a sample, we got 35%. We said, okay, from just our sample of 40 people, we didn't test a bunch, just only 40%, we think the number's close to 35%. Then we figure out our critical value, and we use that in the margin of error calculation to figure out how much room for error do we have. Well, we have 14% room for error. So even though we think it's 35%, we have to allow that it might go all the way up to 49%, or all the way down to 20.2%. So the real value could be anywhere in there from 20 to 49. And you can see why this would be super helpful and why most people use a bigger sample size, because that's a big range. But at least you know it's somewhere in there. Now, yeah, again, if I want a more exact number, I'm going to sample more people. Because the more people I sample, the smaller this range will become, and the better my comfortably usable. That's what we call a confidence interval. So confidence interval, I'm 95% certain the actual percentage of people with this attribute is in this range, between 20 and almost 50%. It's going to be in there. I'm going to be 95% confident. I'm not really going to believe you tell me it's like 60 or 70 or 80%, because I'm going to say that's outside my interval. And I'm pretty confident. I'm 95% sure the real number is going to be within this range. I don't know what it is, but I'm guessing. I'm 95% sure it's in this range, somewhere in here, within these values. Again, if I go back and I did a bigger sample and got a smaller margin of error, I'd get a smaller confidence interval. I'd be much happier with my confidence interval. This one's just really wide because I had a small sample size, only 40 people. Okay, let's try one more. Do it again. Okay, so here they give us, they say it's a simple random sample, binomial distribution conditions. So that's just their way of saying, hey, those conditions are met, so you can build a confidence interval. The one other thing, remember that the number of successes and number of failures have to be at least 5. Well, here you can see that we have 18 successes out of 45 people. And since 18 is less than half of 45, we know that more than half of them failed. So n minus x is actually still going to be okay too, right? N minus x would be 45 minus 18, and that's going to be like 27. And since both of those are bigger than 5, we're good to go. That's what they're talking about here, the requirements that need to be met. As long as you have those simple random sample, binomial distribution, and both of these are bigger than 5, you're good to go. We can do the problem. And the big thing is to watch out for every once in a while you might see one where they give you only like 3 of these or 2 of these. And then you say, oh, I can't do it. I can't do a constant interval unless both of these numbers are bigger than 5. Okay, first off, find our p-hat, because that's our point estimate. Remember, p-hat is always x, which is 18, divided by n, which is 45. So divide those to get our point estimate. So this is just our estimate for our sample. This is like what we think it is based on our sample. So our sample, 18 divided by 45, tells us it's about 40%. So 0.4. So we think the percentage of people for this population is about 40%. But we have some margin of error, right? So we need some wiggle room. So we're going to build that margin of error. So first we need to figure out the critical values. So we need to find out these z's. What is z of alpha over 2? To do this, we look at the confidence level. Remember the confidence level, 95%. So there's going to be 0.95 or 95% in the middle. If there's 95% level, there's 5% left over between the two halves. So I cut it in half, I get 0.025, which is 2.5% in each half. So I'm looking for the z-score that corresponds to 0.025. Again, this one you can look up, or you could do the inverse norm. So if you forget to look it up, you can always do the second inverse norm, 0.025. Not too hard to do. It gives me the negative, but I don't want the positive number, so I'm going to say that this is 1.96. Because when we're using the margin of error, we always want the positive critical value, not the negative one. We don't want to use the negative one because we don't want margin of error to be negative. We want it to be positive. So we use 1.96, even though I found this value, which negative z of alpha over 2 is negative 1.96. But we want this number. That's what we're going to use. The margin of error, remember, is the z-score for the alpha over 2 and the square root of p hat over times q hat over n. So this one we found 1.96 for z of alpha over 2, so 1.96. So anytime they do 95% confidence level, that's going to be your z of alpha over 2. That doesn't change. P hat we said is 40%. So we got 40%. Well, if it's 0.4 or 40% for the p hat, what's q hat? Remember, it's the opposite, so it's the other 60%, so it's the 0.60. And then n is the sample size, which in this case is 45 on the bottom. Again, we don't have a very big sample, so I'm going to expect kind of a big margin of error again. Because what is it? Let's type it in. 1.96 times second square root, 0.4 times 0.6 divided by 45. And we get 0.14. So not that different, right? It's still pretty close to what we got in the last one. It's 0.143 or 14.3%. That's our margin of error. That's how much error we have. Now the last step is to build our confidence interval. And remember to find our confidence interval, we take the p hat and we add and subtract the margin of error. So p hat we said is 40%. That's our percentage that have the characteristic, the percentage of success, and we add and subtract this 14%. So we're going to do 40% plus or minus 14.3%. That's how this is going to work. So if I subtract 14.3, I get, what's that, 25.7. And if I add 14.3, I get 54.3%. And that is our confidence interval. Okay. Now I ran through it like this because it's good to understand what's going on. We need to know what the process is. What are we even doing? And the idea is we're finding an estimate. We're finding one single value that gives us a guess about what the value is for the whole population. We find our margin of error. I like to call it the wiggle room. It's like we need to have some wiggle room because we know our answer is not perfect. So how much wiggle room do we need? And again, that's based on our sample size and our confidence level and all that. Once we get our wiggle room, we use that. We combine it with our point estimate to build our confidence interval. And that gives us our wiggle, our final, like, okay, within this range, we are 95% confident the value is within this range. But you don't have to do this whole process to find the confidence interval. You can find the confidence interval just using your calculator. Because, of course, this calculator does everything, and it does find confidence intervals for you. So if you're doing a proportion question like this, where you have x and n, you're finding proportion, you can do the stat button and go to the calculate option. And this has a bunch of different things for calculating confidence intervals. So if I scroll down far enough, I'll see one that says, oops, I hit, oh, sorry, not calculate, it's tests. And it's been I think it's been a year since I've done this, so I went to the wrong option. It's test. Test has all the z intervals and stuff. So to do this, we're going to go down all the way till it says 1 prop z interval. Why does it say 1 prop and z interval? Well, 1, because we're only using one set of data. Later in the semester, we'll have situations where we might be working with multiple sets of data. That's why we'll say 2 sometimes, because we have 2 sets of data. Prop stands for proportion, which is what we're doing when they have x over n, and you're going to calculate the proportion like this. It's a proportion. And z interval, because we're going to build a confidence interval using z-scores. So to use a calculator, on the calculator, we're going to do 1 prop z int. So that's the 1 prop z int, and it's under stat and then tests. That's how you get to it. So you hit the stat button, you go to tests, scroll down until you get to 1 prop z interval, hit enter. Mine's fancy, so it lets you put the numbers in, so I could put the x in, which is 18, right? So 18 we have, put that in, enter. N is 45, I put that in, enter. The confidence level, 95%, so we put in 0.95. Like I said, that's really common, that's why it was already in there. And then we calculate, and it gives us the confidence level, the confidence interval. So that confidence interval we have right here, 25.7 and 54.3. There it is, 25.7 if you round it, 54.3. Also gives us p hat. So there's that p hat that we just figured out by ourselves. Does it for you. It gives you 45, which we gave it. That gives you that information. Notice it does not give you margin of error. So if you want to find margin of error, yeah, you could still use this to find margin of error. Note also though, the margin of error is just half this distance. So if you find out how far apart these numbers are and divide it by 2, that's another way to find the margin of error. So you actually can use this to find both the constant interval and the margin of error. If you need the critical value, well, it doesn't find the critical value for you. So you'd still have to find the critical value. So that's something you'd have to be able to do on yourself, on your own. So this one, again, we said x is 18, n was 45, and the confidence level is 0.95. And then they gave us the 0.2569 to 0.5431, which is the same thing, right? Just as decimal instead of percent. So if you have, how many successes, the sample size, and the confidence level, you can just throw in the calculator and get the confidence interval. Okay. Now what if you don't have that information? What if you have the confidence interval, but you need to go back and figure out the point estimate and the margin of error? So this is something you can actually work a little bit backwards. So sometimes you might know the confidence interval. Maybe you looked it up in online and you know it, but you want to know the point estimate or the margin of error. So like when you use the calculator, right, it gives you a confidence interval. It doesn't give you the point estimate and the margin of error. In this case, we'll use those endpoints of your confidence interval and go back and find that information. So the point estimate, notice, is always the midpoint. It's the middle number between the ends of the confidence interval. So you can find the point estimate by just taking the two ends of the interval, adding them up, and dividing by 2, because that's how we find the middle. This is like finding the average, right? Remember, average, you add up the numbers and divide by how many there are. So that's what we're doing. We just average them out and now find the point estimate. So this will find the middle number for you. So if you have the calculator's, confidence interval, but you need to find the point estimate, you can do that. Though again, the calculator does actually give you the point estimate, so it's not super useful unless maybe it's a situation where like you looked up the confidence interval. The next one is what if you want the margin of error? Well, since the interval is always twice the margin of error, you can subtract to find the length, how long is the interval, and divide by 2 to get the margin of error. So these are two things your calculator doesn't do for you. So if you're going to put something on your sheet, you might want to put this on there as a reminder how to find the point estimate or how to find the margin of error if you know the confidence interval. So this is from the confidence interval. We know the confidence interval. We're looking for the point estimate or the margin of error. So for example, a magazine says somewhere between 45.8 to 46.5% of millennials hadn't read a physical book in the last year. So this is our confidence interval, right? That's our confidence interval. That's our confidence interval because they gave us the 45.8 to 46.5. So the confidence interval is 45.8 to 46.5. But what they didn't tell us is they didn't tell us what percentage they got when they did their study, and they didn't tell us what our margin of error is. So we're going to find the percentage ourselves and the margin of error ourselves, using those formulas up here. So first off, to find the point estimate, we add the two numbers. So I'm going to take 45.8 plus 46.5, and then divide that by 2. So add them up, divide by 2. So I do 45.8 plus 46.5, add them up, and then divide by 2, and I see that 46.15 is actually what they got. That's the percentage, their point estimate, or p hat. So that's the middle number between these two. It should be literally in the middle. That's their point estimate. To find the margin of error, we subtract. So I do 45.8. Actually, I should do the top minus bottom because I want to get a positive number. So I'm going to do 46.5 minus 45.8. We always want to do top minus bottom because that way you get a positive. If you get a negative margin of error, not a big deal. Just get rid of the sign because you just need a positive. So if you flip these around, you'll get negatives turn into positive because margin of error should always be positive. So if you do get a negative, it just means you put them in backwards. So if I do that, if I do 46.5 minus 45.8, that tells me how far apart the numbers are. That's the length of the interval, but I divide it by 2, and that tells me what the margin of error is. So in this case, margin of error is 0.35. It's pretty high, 0.35. So this makes me look at it and go, they had a 35%. Oh no, this is 0.35%. This is percent. It already is percent, right? So that's not that bad. 0.35 is pretty small. I was thinking it's 35%, but it's 0.35%. So that's not bad at all. That's a pretty small margin of error. So I would trust their data. They probably did a big sample if they only have a 30.35% margin of error. So that says, okay, yeah, this is good information. I'm going to trust that. You know, they had a sample to get from 46%, and they only had 0.35% margin of error. The one thing is maybe they're really unconfident, so they could have done this with like a 80% confidence level, and that might be one reason to get a low margin of error. But if they did a big sample size, I'd probably trust their data. So that's why in real life, if you're going to really depend on someone's study, you really want their information. You want their confidence level and their sample size and that kind of stuff. But if you don't have it, you can at least kind of figure out the point estimate and the margin of error just from their confidence interval. So again, let's just use the calculator to find the confidence interval and then go back and find p hat and e for margin of error from that confidence interval. So if you have the confidence interval, you can always go back and find that information. So as far as doing your homework and stuff, you might not actually do a lot of finding the margin of error by hand, because a lot of times it might just be easier to find the confidence interval and then go back and get the margin of error for this section. Okay, last thing before we're done with this section. So, oh, I got 2 pages. Wow. For some reason, I was thinking I had less pages than I thought. I'm going to finish, and I got 2 pages left. I didn't look at my notes close enough, I guess. Okay. So next section, so testing claims. So a lot of times people will make claims about data, about information sets, and you can actually kind of test those claims by building a confidence interval. So a confidence interval can be used to make judgments of claims about a population's percentage. For example, if someone says that 60% of a population has health insurance, and you build a confidence interval from data you collect, and it's 45 to 55%, then you can reject their claim. You say, hey, you're full of you know what, because my statistically collected data, my sample that I went out and collected, says that no, I should only expect 45 to 55. You said 60%. That's way over. You are overestimating the percentage of people that have health insurance. And people do this. This is how you really go out and test things. Is you collect sample data, build a confidence interval, and then check is there value they claimed in your confidence interval. If it's not, throw it out. So we're going to say, if appropriate, find the confidence interval. So we're going to find the confidence interval. These data tell us it's simple random sample. That's just making sure it meets the requirement. It is a binomial distribution, which is good. We have 38 positive results and a group of 40 test subjects at the 95% level. Notice right here, this is where you can hopefully get a little bit of a red flag, because you see that there are 38 positive results, which would be X, right? So X is 38. And you have a group of 40 test subjects. So N is 40. And I told you that every once in a while, I might throw this to you, I might give you a situation where both X and N minus X are not bigger than 5, right? We always had that to meet the requirements. X is fine, because X is bigger than 5, 38 is bigger than 5. But if I subtract those, if I do 40 minus 38, that's only 2. And that is not bigger than 5. So in this case, it says if appropriate, the answer is not appropriate. 2 few failures. So there wasn't enough failures. We need to have more than 5 failures. So this tells us they need to go back and they need to take a bigger sample. Their sample has to be so big they get at least 5 failures. So 40 wasn't a big enough test group in this situation. You need to go big and get more of them. You only got 2 failures out of 40, so I'd say probably more than double your test group and see if you finally get enough failures to go do the test. So in this case, we couldn't do it. So let's try one where you can, because that was just a reminder that you have to check that X and N minus X bigger than 5. Let's try this one. Okay, this is, again, simple random sample, which is great. Binomial distribution, which we're looking for. They say out of 50 people surveyed, so N is 50, 28 of them were employed full-time, so X is 28. And that one is bigger than 5, so that checks out there. What's N minus X in this case? Well, N minus X is going to be 50 minus 28, which would be 22. And that's also bigger than 5, so that checks out. So that tells us, okay, it is appropriate this time. You're allowed to do the confidence interval. Okay. we want to do a confidence interval with a 90% confidence level, and then they want to say, is it reasonable to claim 55% of the population have full-time employment? So I'm going to use that one prop z interval on my calculator. I'm going to put in x is 28. I'm going to put in n is 50. I'm going to put in my confidence level. So confidence level is 0.9, and we'll see what we get. So again, we're not going to do all the hand stuff because we can just make the calculator do it. So let's make our lives a little bit easier. But again, remember what the calculator is doing is it's finding that margin of error, it's using the critical values, eventually building this confidence level. So 28, 50, 0.9. This one would have different critical values because of 0.9. Remember that the confidence level changes the critical values. Okay, so this one ends up with an answer of 0.4445 to 0.6755, or 44.45% to 67.55%. I wanted to turn it into percent because notice the value they give us is in percent, right? They're looking at 55%. Is 55% valid? Well, if I look at my interval from 44 to 67%, yeah, 55% is in there. So yes, it contains 55%, so it is reasonable. Now, if they'd come at me with 70% or 30%, I would throw them out and say, nope, it doesn't work. Your value is not reasonable. It doesn't seem right. But because their result is in my range that I got to let it fly. I got to say, oh yeah, that's okay. Yeah, that's good enough. Yeah, I only got, what did they say? My proportion, I got 56%, which is actually a bit higher. So I got 56%, but your value is close enough to what I got. I'm going to let it fly. I'm going to let it slide. My margin of error is wide enough that it, my interval contains 50%, 5%, so it's reasonable. And this is what people do. People do this all the time in real life. If someone makes a claim about a population and they want to test that claim, they go out and they gather data, construct their own confidence interval, and check. Does that person's value fall in my confidence interval? If it does, I'll let it fly and say, yep, it's reasonable because it falls in what I got. But if I go out and I test it and their value's way outside my confidence interval, I'm going to say, no, your value doesn't make sense because I did a study and it doesn't show the same thing. Now, of course, everybody's studies can be a little different because everybody's samples are different. So they might still actually be accurate with a different sample, but this is a way you can kind of double check them. Now we're on the last page. Sorry about the last thing. Okay, so there are times when you have a really small pool of candidates or you don't have a lot of money, you want to save your money. So you might need to make sure that your sample is large enough, but try and keep it as small as you can. So a lot of times we want to check and make sure a large enough sample to obtain our desired margin of error, because we want to have a small enough margin of error so we don't have a huge confidence interval, and actually have our confidence level, because you want to make sure we hit that 95% confidence level, whatever level we're go for. So in this case, we're actually using this formula. So this is a formula that will find the sample size based on what your margin of error needs to be and what your confidence level needs to be. So that's what this is doing. So we're looking for a large enough sample given a desired margin of error and confidence level. And that's the formula for sample size n. Now, this works great if you have a good guess. This is when we have a guess for what the percentage is going to be. So maybe you've done a similar study before in the past, so you kind of have an idea. So like 5 years ago, I did a study on health insurance, and so now I have an educated guess on what I expect the percentage to be. Then we'd use this formula. If you don't have an educated guess, there's another formula, which is this one down here. It's again to find sample size, but in this one, instead of using p hat and q hat guesses, so this is a guess for p hat, and then the corresponding q hat. Instead, in this case, they just use 0.5 for both of them, which is kind of 50%, so that's kind of a middle of the road. And then if you use 0.5 for both of them, it multiplies to give you 0.25. And so this one doesn't have a guess, it's just a kind of blanket estimate. This one is going to give you kind of a larger n. It's going to give you like the biggest n possible, basically. This one's going to give you a smaller n, typically. So we'll use this one as much as we can when we have a good guess, and this will be when we don't have a guess. So this is with guess for p hat. This is without guess for p hat. And these will always give you, like decimals typically give you decimals, so you always want to round up to the nearest whole number. Don't round down, no matter what the decimal is, always round up, because you want to make sure you have enough people. If you round off the half person, then your sample won't be big enough. So you always want to round up to make sure you have enough people. So let's do it. We'll do two. We'll do one with an educated guess, and then we'll do one without. So they'll give you information. They'll give you the margin of error, right? That's our E. The confidence level, that's our, our confidence level, which we'll use to get the critical values, and then the educated guess, which is going to be our p hat. So first off, to get that z of alpha over 2, I have to think about the fact that if this is 95%, then alpha is 0.05 or 5%, and alpha over 2 is 0.025 or 2.5%. So to find this, we're going to find z of alpha over 2. So you can either look it up on the chart, or you can go back and use that inverse norm with a 0.025, which I still have in here, so I'm just going to enter on that, and it is still 1.96. This is 1.96 because I used inverse norm with a 0.02501, and then I just made it positive, right? So I get positive 1, this becomes positive 1.96. So we only want positive alpha, so we want a positive alpha for this as well. Okay, and then Q hat, notice the P hat is 47%, the Q hat would be the opposite, so it would be 53%, because they should always add up to 100%. So that's what I need for my formula. So my formula for n is going to be alpha over 2, which is 1.96, squared, times P hat, which is 47, so 0.47, times Q hat, which is 53, so 0.53, all of that over n, which is our samples, or sorry, not n, our over E, which is our margin of error, 0.14 squared. Now give us our sample size. So that's how we get the sample size. So this is one of the formulas that's not in your calculator, so you do need to write this down if you want to be able to do this. So put that in your formula sheet, and then just know how to find those different values. Again, it's good to know how to find those critical values, which if you have written them down for the standard ones, that helps too. Okay, so we have 1.96 squared times 0.47 times 0.53 and then divided by 0.14 squared. Squares will happen first. You put it in this order, multiplication happens before you divide, which is what we want, right? Multiplication before division. So you really don't need any parentheses, so you can just type it in just like that and get your answer, which in this case is 48.8. But again, we always round it up, so we get 49. So you need to have at least 49 sampled. So if you're doing this study, if you only study like 47, 46, you're not going to have enough people for the margin of error you want. So you have to have at least 49 people in your study to get a big enough margin of error at that confidence level. If you had a lower confidence level, then you, again, wouldn't need as many people. Or if you're at a higher confidence level, you need more people. But if I want this confidence level and that margin of error, I need at least that many people sample. Usually, if you get more people, that's great because it just means your margin of error gets smaller. And usually, people don't mind a smaller margin of error. It's just when it gets too big that you're in trouble. Let's try one more. This time, there's no educated guess. So now we don't use the first formula because we don't know what to put in for P hat or Q hat. So instead, we're just going to put 0.25 for the combination for those two together. So this is only when there's no guess. So we don't have a guess, no guess. We use the other formula. This time we're using confidence level of 99%. Margin of error is 0.12. So the confidence level has changed, so our alpha is different. So alpha is now 0.01, and alpha over 2 is 0.005. So if I want to find z of alpha over 2, I'm going to do that same inverse norm, but now I'm going to put 0.005 in here. And now it'll give me my value. So it gives me a negative 2.575, but remember that that turns into positive if I want the z, the positive z. So I'm going to do positive 2.57, I guess 6 if you round that up. 576. I forgot the 7. 576. So I'll use that for my z alpha over 2. So that's my z score that I'm going to use. So when I do my formula, my z score, z of alpha over 2, is going to be 2.576 Again, that is squared because of the formula. 0.25 is what I put in here, so I put 0.25 in there. And then on the bottom I have the margin of error, E, which is 0.12 squared. So that's what I should get. I get a 2.576 is from my z-score based on the confidence level. So this only changes because my confidence level changed. I went from 95 to 99. That's why I had a different value. 0.25 because there's no guess. That's why I used the 0.25. And then 0.12 is from the margin of error. So that gives me my value. So I put 2.576, square it, times 0.25, divided by 0.12, and square the 12. So I get 115. So this one, you'll notice I need a lot more people. And it makes sense because I had a higher confidence level. The bigger your confidence level, the more people you're going to need. I also wanted a smaller margin of error. So it really makes sense to need more people. But again, I wouldn't stop here. I would definitely round that up to 116. Because I don't want to round off that 0.2 person, because if I do that, I'm not going to end up with the right value. So I need to have enough people that 99% I still only have 0.12. So if I did like 115, this would be like 0.122 or 0.123. It'd be too much. So I have to have at least 116 people in my survey. If I survey more than that, I'm happy. Anything more than 116 is going to be great because it's just going to decrease the margin of error. But I need to survey at least 116 people. So this is what statisticians do. If they have requirements, the boss says, okay, when you do your study, you need to have a margin of error of no bigger than 10%, and I want you to use a 95% confidence interval. And so then they go and they figure, okay, how many people do I have to get in my study? And then they make sure they get at least that many people surveyed before they do their work. Okay, so that's it for this section. So again, this section is all about this idea of building confidence intervals. So we take a point estimate, which again is the value from your sample results, your sample data. You calculate the sample result, and then find the margin of error so you can build a little window. And you make this window where you're 95% or whatever confident that the real value is in that window. We're going to do the same thing again on the next section, but the big difference is instead of working with proportions, which are percentages, we're going to work with means. Now it does get a little trickier with means, which is why I saved that for second, because the calculations get a little bit harder, but it's the same idea. So we'll be doing more confidence intervals on the next set, just with means instead of proportions. So that's it for this section, and I'll see you on the next set.